Okay, so in this particular lecture, what we're going to talk about is star spectra and kind of how we interpret information from stars and why that information is the way it is. So the first thing we have to do is we have to talk about what is called a continuous spectra, which a continuous spectra, we're very familiar with this idea because it's this idea of a rainbow. A rainbow is an example of a continuous spectra. So the way it works is we have some sort of light, and those light waves travel through a prism. They bounce around a whole lot and come out in different wavelengths than they went in. So light is made up of a mixture of wavelengths. So we have this white light. We have this white light that goes in. It goes into some sort of prism, what we call diffraction, okay, which you should have learned about in your physics classes. We have diffraction, and then we have separate wavelengths. Separate wavelengths. Now, this is called a continuous spectra because the separate wavelengths blend together once they're separated. And when I say blend together, what I mean is that we're separating the wavelengths at such a finite scale, at such a small scale, that they rub up to each other and look like they're continuous colors, which is why we call it a continuous spectrum. So any sort of light that's given off can be broken up by diffraction into separate wavelengths so that we can study the light. And that's the idea that leads us to emission spectra. So you have this idea of a hot gas, an ionized element. Something. It could be hydrogen, it could be helium, it could be lithium, it could be iron, whatever. You have some sort of hot ionized element. It's very high energy. Okay? So very high energy particles. They emit light. They emit some sort of light that's mixed around. It gets diffracted in the prism, but instead of getting a whole bunch of lights, we get specific lights. We get specific wavelengths. Okay? And the way this works is we have an atom, okay, that has its electrons around it, and you'll talk about this more in chemistry. But as light goes into it, it bumps electrons up to another level. Okay? And then it releases that light when the electrons go down a level. So when the electron hops between rings, quote unquote, it's absorbing specific energy. And when it hops down, it's releasing specific energy. So emission spectra are only specific wavelengths unique to an element. Well, we're going to deal with just elements. I mean, you can get an emission spectra for molecules, but we're only going to deal with emission spectra specifically for elements. Okay? So you have this hot ionized gas that passes through some sort of prism, and out pops those separate individual wavelengths again, but they are unique wavelengths to the element. Not every element gives off 500 nanometers or 650 nanometers. Not every element gives off those specific wavelengths. So if we know the wavelengths, we can identify the element. Or substance. For those of you wanting to take chemistry or this a step further, you can identify substances by their emission spectra. Okay? Now, what does this have to do with stars? When we have stars, we have some sort of light here. This star is giving off some sort of light, which is continuous. Okay? So it gives off a continuous light. But then it passes through some sort of cold gas. Now that cold gas could be anything in space. It could even be, interstellar gas from a nearby nebula. It could be even the atmosphere of the star itself. It could be the atmosphere, the gases in the atmosphere. It could be the atmosphere on the planet that we're getting the absorptions, that we're getting the reading on. So this cold gas acts like sort of a filter. Okay? And what happens is it filters out. Wow, that totally didn't come out right. It filters specific wavelengths based on composition of the gas. Now we have to keep in mind that most stellar gases are composed of hydrogen and helium. So they're going to absorb things in the hydrogen-helium range. Okay? But we still pass that whole light. Remember, we've got the whole light here. It gets filtered a little bit. Okay? It diffracts just like the continuous spectra until we get the absorption spectra. Now, an absorption spectra, you'll notice, has these little black lines right here. Okay? That is the part that got absorbed. And it's interesting because we can identify which elements are in the gas that it passed through. Okay? And we can identify what elements are giving it off. Okay? So the fact that we have these wavelengths means that element X is present. The fact we have these wavelengths means that element Y is present. And the fact that we have black lines here means that the gas has element Z present. So if we already know what element Z is, we can kind of filter it out. So that's the gist of spectra, the three different types of spectra we're going to talk about. But now let's talk about how we do it with stars, or what does this have to do with stars? So here I have a star. In fact, I have the sun because the sun is awesome. And we notice that it gives off a continuous spectrum. Okay? So it's just like turning on a light bulb. It gives off all wavelengths of light all the time. Okay? However, as it passes through its atmosphere, as it passes through gases in space, some gets absorbed. So we are left with an absorption spectrum. There's also gases on Earth. We have an atmosphere that acts as a filter. So the absorption spectra looks a little different on Earth than it would be coming right off the sun. So we see more darker bands in the continuous spectrum as gases from Earth's atmosphere absorb light too. Okay, so basically, if we take the absorption spectra on Earth, the on-Earth spectra, which I'm going to abbreviate, we subtract the gases, the Earth gases. If we subtract the sun's gases, we are left with the spectra of the sun. So that allows us to identify what the sun is made of, what the sun is doing. Now, just to give you a little taste of things, Here's what an absorption spectra actually looks like. Okay, you'll notice it goes from blue on this end to red on this end. Okay, we've talked about red shift and blue shift before, so shouldn't be too unknown. We're using the colors of the rainbow essentially. And basically what this means is, okay, at 434 nanometers, that means hydrogen, a specific type of hydrogen is present. At 430 nanometers, there's another black line that says iron is present. And at 430.774, there's another black line. Let me do this instead. That indicates calcium is present. So these black lines right here, these little shade lines, okay, allow us to determine what element is present. Now, elements are usually made up of more than one line. For example, if we look at iron, 430, we'll say this is iron right here, okay? But as we look over here, we see at 495, there's another little line that says iron. And then at 527, there's another little line, okay? That means those three, the presence of those three lines, or instead their absorption lines, indicates that iron is present in whatever star this came from. Okay? The same is true for things like calcium or magnesium or sodium. And in fact here, there's this very faint dark line you may be able to see, may not, it's right here. Okay? That says terrestrial oxygen. If we were to remove that, or that tells us what gases are absorbing it in the atmosphere. So that's a line we would cancel out to get the spectra of the star. Okay? These lines indicate which elements are present in the star. Now let's talk about something a little bit more complicated. There's this big screen right here, it just popped up. You don't have to read it all. Of course, you can pause it and read it if you want to. But basically, we use the spectral classification. We use the spectra to figure out tons of things. We use it to figure out the temperature, most importantly. And from that, we can figure out other features of the star. And from that, we can figure out things like the mass, the radius, the luminosity. And then this thing right here we're going to talk about later called the main sequence lifetime. Okay? But most importantly, I want to draw your attention to this idea. Okay? We use the spectral class, or we use the spectrum of a star to figure out what elements are present. And if we can figure out what elements are present, we can figure out how hot the star is. Okay? Heavier elements like calcium, iron, and titanium correspond to this 2500 to 5500 temperature range. Whereas lots of helium right here corresponds to 30,000 or more. And that is because the temperature is relative to the type of elements that are produced. Hotter stars produce lighter elements. They're capable of fusing lighter elements into heavier elements, but cooler stars are not. Okay? It goes back to that idea of the cycle of elements that are forming by fusion and fission. Okay? Once the star cools down sufficiently, it can no longer cycle those elements through. And if it can't cycle them, that's when we see them. So the elements that are produced are dependent on the temperature of the star. So we can say ipso facto that the spectra of a star is an indication of its temperature. And I don't know where to write that. That's not writing over stuff, so I'll just write it here. The spectra I'm trying to think of the best way to say this. The spectra indicates the temperature of the star. And as we will see in later lectures, this temperature of the star indicates its life, where it's at in its life cycle and things like that. So if you have any questions, feel free to comment below or send me an email or talk to me in class and we will get them answered.